due to a few call-outs, we'll be doing a drill during lunch. Hope you guys don't mind. Thanks for still participating. Due to some technical difficulties, we have to re-go over some stuff. So we'll go over nice and quickly since we've already done one of this morning. Alright, so today's drill, OH&S safety considerations. Exits, just to my left here at the engine bay door, just to my right. Bathrooms are just go to the back and to the left if you need to go. Trip hazards, if you need to get up to do anything or put rubbish in the bin, just watch the trip hazards. And correct PPE when using the electrical safety kit. Today's learning objectives and outcomes. So by the end of this drill, hopefully you're more familiar with the theory behind the body walk and the mini rescue. So hopefully you're more proficient in basic operations of the body walk. Hopefully you learn more about electricity and why it's a hazard. And hopefully we can improve safety around electricity in general. Today's lesson content, so we'll look at basically in this order, what is electricity? I know a lot of you guys already have a strong knowledge about jobs and electricity, but if we just refresh what electricity actually is and why it's so dangerous. Basic operations and safety considerations, use of the bodywork, safe working practices, demonstration where you'll have a quick go, which we've already done this morning, but we'll do again, and maintenance of the electrical safety kit. So let's go over the basics of what electricity is. Electricity is a form of energy and is the flow of electrons. All matter is made up of atoms, and an atom has a center called a nucleus. The nucleus contains positively charged particles called protons and uncharged particles called neutrons. Electricity is measured in units of power called watts. Kilowatt represents 1,000 watts, and 1 kilowatt per hour is equal to the energy of 1,000 watts working for 1 hour. Okay, so we'll just look at some of the different terms in relation to electricity. We'll start with voltage. So voltage is measured in volts, has a similar effect to pressure on water in a hose. The higher the voltage or the pressure, the further electricity can travel for the transmission of electricity over long distances. Power stations level high voltage at typically 332 kilovolts to a destination. So, as we mentioned earlier, if we get called to a power station or substation, we need to seek permission of the electrical authority before we enter the grounds for safety. It's the same thing if there's like an animal rescue in a substation, we leave the animal there until it's safe for us to enter, with safety being our number one priority. Okay, another term we need to look at is current. This is the flow of electrons through electrical conductor and is measured in amps. Current is similar to the flow of water, like litres per minute in a hose. The more amps the flow, combined with voltage, the greater the power to work. So volts would be the pressure in a hose, in that example, and current would be like the literage per minute. So the more current, more electricity coming out. Yeah. Resistance. This is the effect conductor material size and length has on allowing electricity to flow and is measured in ohms. Resistance is friction loss, the white friction loss in a hose, with larger diameter hose being more efficient at pumping water, and similar to electricity, you see that if it's got a larger area, you will get larger electricity coming out. Conductors and insulating material. So a conductor is a material that allows electricity to flow through it. Different materials vary in their conductivity. Metals, for example, are highly conductive. Materials that offer high resistivity, like ceramics, are considered insulators. Examples of conductors, metals, they're pretty common. See a metal, don't get any electricity. Human body, timbers, flames and dense smoke. So if we look back at bushfires, we don't want to get pumped too close to power lines because the smoke can act as a conductor and get plasma strikes. Some fire extinguishing mediums, for example foam, you can still get electricity current go through it. Wet or dirty rope or dirty water, including hose lines. Electrical safety devices. So we look at some of the different devices we might see at jobs. These include fuses. You can see the picture. This is a link placed in the electrical circuit that is designed to fail when the flow of current is excessive and causes the circuit to heat up. So So basically, once the fuse blows, it will stop the circuit from being connected, and will hopefully stop the electricity causing further damage. We have a circuit breaker here. We saw these at the job this morning. Performs similar function to a fuse. It has the added advantage of once being triggered, the cause can be identified and it can be repaired, and then the breaker can be reset. It also has been activated like a switch to isolate the circuit it protects. This one here is a safety switch, earth leakage circuit breaker or residual current device. The safety device can detect certain electrical faults and shut off the circuit to minimise harm. So you'll especially see these in things like rooms where you have like computers and stuff, where if there is damage for electricity, you're not going to lose the whole circuit. We've got a switchboard here. So switchboards are a junction of the main supply from the electricity network and the consumer. They range from a small residential switchboard, or as one we saw today, a switchboard in a larger building or factory. The voltage range normally is between 240, which is your common appliance voltage, to 415 volts. Okay, so one of the reasons we're doing this drill today is because of the extreme harm electricity can cause if we come in contact with it. So the effects on the human body include, if experienced with extreme electricity conducting through the body, the effect of the body depends on the amount of current and the length of time the body is exposed to the current. So it's the current, not the voltage, that kills you or does damage. Alright, so I've got a little picture here which shows some different impacts of the human body. As you can see, we've got stopped breathing, cardiac arrest, ventricular fibrillation, involuntary muscle reaction, and electrical burns from the current. So we'll look at a video a bit later which shows you what happens if you touch an electrical wire and the burning and the actual smoke which comes out of the body. Alright, a warning, only 75 to 300 milliamps is required for ventricular fibrillation, and anywhere above 300 death is almost certain. The average residential distribution system carries 13,000 times this current. So when you look at it like that, you don't really need to come into contact with it too much to have a catastrophic outcome. Alright, so how do electrical shocks occur? We've got two main ways: direct contact, so if you actually touch the electricity on the wire or whatever's stimulating electricity, or indirect contact. We look at things like step potential, where it goes through the ground and or goes through the air. So indirect contact might be, as the example spoken before, at a bushfire. Take note that the voltage gradient varies depending on composition of the ground, moisture content, and voltage electrical source. Okay, step potential. So we'll just do a quick demonstration of the board. So we've all looked at step potential, yep. So basically, wires come down onto the floor. We have what's like a ripple effect, where the electricity is at different voltages depending on how far away you are from the electrical source. So we've got another visual image here, which everyone can see. Has the examples of if you're standing in two different areas of the ground with different voltage, then you will have current go through you. And as we said, it doesn't take much current in order to cause serious harm or death. Isolating versus turning off power. So another terms that are commonly confused with vibrators, they sound very similar. So isolating the power is when the electric company, and only the electric company, can isolate the power, so they will disconnect the power source to the building. Turning off the power is when the station officer or one of us goes up to the switchboard and switches it off the mains. Take note that when the SO says that the tower has been turned off, that's all that's happened. There still might be electricity being fed to the building. When it's been isolated, we know that power has been switched off. The little tricky thing here is with the new solar systems going up, that's a lot of the time that can be isolated, but you still have residual energy or electricity in the system. And with solar systems as well, even once it's switched off, you still might open up your hose inside and still end up getting electric shock. So if you do see solar panels on the roof at a building fire, please be careful. Okay, communication. So when power's being turned off, it's important that it's communicated properly. It's very imperative for the SO, but good for us to know as well. So all personnel in incident grounds should be notified of any live electricity hazard. So if we're inside a building or at a job, we notice it, no one else has, get on the radio and let the incident controller know. All personnel at the incident and the ComSend when the power has been turned off, so let the comms know. And personnel at incident grounds should also let comms know if it's been isolated. Okay, so just looking at some different situations where you might not rush to turn the power off. This includes if you're going to a health place, so basically like a hospital or something where you've got people on dialysis, or if you go to an industrial complex where you might have gates and stuff which control electricity, and by turning that off you might trap yourself in there. So there was a case in Raldemere a couple of months ago where the fire went into the underground car park, power was turned off, the automatic gate closed, and the only way to get out was a manual override, which they couldn't see in the thick smoke. The other one is high-rise buildings, so you've got to make sure that the lifts and other sort of airway systems are still going to be working on a residual power, otherwise you might be cutting off people's escape routes. Okay, so the main piece of equipment we're looking at today is electrical safety kit. As I said, we've been through this earlier this morning before the technical difficulty with the camera, so we'll just go through it quickly. Contents include screen bag of the made of canvas. It has 3 separate compartments, which you can see. Have the gloves separated so that they don't get damaged or rub against each other, causing holes and minimising their effectiveness. The gloves are to be stored separately due to that reason. They are rated to 650 volts, but if they are damaged, that the rating minimises or decreases. Okay, so leather gloves don't actually give you any sort of protection from electricity, but they do protect the rubber gloves. So important to use them, especially so the next person who uses it don't have a reduced effect. The voltage detector, or the Modi Walk. So it's officially called the GLN Mini Rescue, but according to the sim sheet, we call it the Modi Walk. We'll get into some details on that. It's a small proximity non-contact voltage detector. So basically, for safety reasons, you never grab it and touch it to the electrical source. Weighs about 120 grams, can detect AC voltage, 50 volts to 500 kilovolts in the AC range only, so it will not pick up a direct current. The detector can remain functional in atmospheres -10 degrees to 65 degrees Celsius, which covers most temperatures in Australia. It can be used to determine the location of electrical hazards and structure fires, so going in there, trying to, when you can't see, use this to determine if there is electricity still in the building. But once again, it is not intrinsically safe, so if it's a hazardous atmosphere with gases, it should be used with caution, if at all. Can be used to confirm power has been isolated, or if there's no illegal power system. So, for example, in a drug lab, you might switch off the power in the mains, but they've actually recircuited their neighbour's electricity, and you've got their spray water, and there'll still be electricity in there. So it can be useful for that. Safety officer for ongoing safety checks, incidents, and to identify items or objects liquefied. So, for example, if you've got a car with electrical wire on it, you can use that to determine if the object has electricity still running through it. But even then, extreme caution and waiting for the electrical company is ideal. Safety considerations. Do not hold the Modi Walk in contact with an electrical conductor, as we discussed before. It will not detect direct current, so looking at a train incident where you're waiting to go onto the tracks, make sure you wait for the train company or City Rail to allow you on the tracks before you go on there. It will not detect high voltage. It's not intrinsically safe, so it can spark and light gases. And if the electrical source is in water, the water may impede the detector's ability to detect an AC current. The Modi Walk is to be used with a pair of insulated electrical gloves and the leather gloves, as already discussed. So the sims and maintenance, get it out. You have a 9-volt battery it's powered by, which open the back and can be replaced. Replacement batteries can be found on SCATs. The way to identify if it's flat is, firstly, it's got the LED on the front. If it's orange, it's got low or flat battery. If it's green, it's good to go. The insulated gloves, so the orange gloves need to be replaced every 12 months. They will have a date stamp on them, and then that's their manufacturing date, and then from 12 months from that date stamp, which will write the date it expires, so in this case, February 2017. So making sure that during sims that is tested and checked in order that they can be ordered before the expiry runs out. Okay, so once again we went through this morning. 5 steps to turning off power, we'll just quickly mention them. Don the electrical glass, John general purpose glass, and ensure the helmet visor is down for step 1. Step 2, check the area where the switchboard is safe, so wires hanging down or other hazards, and then identify the main switch or switches in the switchboard. Turning your eyes from the switchboard and using the back of your hand to switch them off is step 3. Step 4 is switch circuit breakers to off and remove the fuses, as looked at in the previous slide. And then step 5 is to send a message to the crew on the fire ground, and then obviously the comms. Okay, so we'll look at these videos. I'll just pause the video while we watch them. So I've got 3 different videos for you to watch. I'll just quickly pause the video and then get back into them.
America?
Yep, in America. So they've got the roof to cut a chimney to ventilate, and as you can see, they haven't taken notice that there's wires above them. Smoke's coming through and it's conductor.
Get off the roof, you dumbasses.
Okay. Here's another one with the electricity too close to the building, ladder too close, and then it all goes bad in a second.
What is that? Why is that wire flipping? What's touching it? Wires?
Yeah, it's a.
You don't have this much.
Basically, one fell through.
Oh, really?
Yeah. Okay, so I've included a quiz to do some learner-centered areas. I'll get you guys to complete that now. Can the body walk to detect both AC and DC?
No.
No, well done. Where is the electrical safety kit stored? OS2. And the last one, what are the 5 main steps, if you can remember? Yep, turning off power.
Look away.
Yep,
Safe area.
Yep.
Safe approach.
yep,
Turn away.
Yep.
Back at hand.
yep,
Glove, glove.
yep, and then communicate
Then
voice.
push the crew the power switched off.
Excellent. Okay. What we'll do is we'll just quickly go over this once more for the video. So checking the sims on these, make sure there's no leaks in them. Rolling it over, getting air traps, listening, hearing. You got that. So you do it on first, checking these for discoloration or chemical damage. And then making sure the actual canvas bag has no damage on it. And the actual Modi walk, when using it, switch it on, the on button here. Test it, we have to push the test button. makes that noise. It's working. Battery's working. Switch to low and high on this button here. Okay, and when using it, holding it an arm's length away, putting our finger on where it says hold here, and going up to the device. So for example, if we got to something with electricity,
That doesn't have electricity. The power bill is not
over here, oh, there we go. So it detects electricity. So what we'll do now is everyone can have a go at that. You can do it on electricity. There's power on there. Switching on, excellent. Well done. So once you finish using it, switch it off, place it back in the protected casing, and good to go. So very good size, it's stored in the front pocket of the gear. And once again, making sure if we're using that as a job, we have gloves on for safety. Alright, any other questions? No? Excellent. Alright, thanks for attending drill. Once again, thanks for suffering through it, second time due to technical difficulties, and have a good afternoon.
Thank you, Robert. Sure, you apologises for his flatulence problems.